All right, so welcome back. So this time, the talk I have is related to runtime system. Basically, things which will affect when you are running the program. And in particular, it is about garbage collection. So I can see annotation has been enabled. So I hope I can make good use of it. All right. So any non-trivial program that you are going to write will require manipulating memory. Okay, and many of these constructs, when you are writing program, you will require variable amount of memory or memory which you cannot predict at compile time. So if you try to guess too much, you might end up lot of space. But if you guess too little, then your program may crash or produce weird results. Okay, so that is why we would like to have some kind of memory management which is dynamic, which happens at runtime rather than fixing it at compile time itself. Okay, so memory, when your compiler is working, it allocates memory for certain constructs. So for example, it creates some space. When I say again create, in a way it just lays out, it just decides that how things will be laid out. Actual allocation or actual assignment will happen at runtime, and again linker loader come into picture at that point. Okay, but what compiler does, it creates kind of a blueprint that this is where global variable x will go, this is where these static variables will go, and code and other stuff, right? So some of the memory is allocated on runtime stack. Again, in this case, compiler just creates offsets with respect to either the start of the place where activation record got allocated, or end or middle, depends on different compilers as well as runtime systems. Okay, but it is with respect to some fixed location. But then there is some memory which cannot be allocated on heap. Can someone tell me why we cannot use a stack for certain kind of memory, a certain especially objects which we allocate ourselves and we want to work with them for a long time? So what is the problem in allocating them on stack? Okay, I see something on chat window. Sizes of objects must be fixed to use the stack. Yashas, this is not necessary. C provides what is called alloc instruction. I mean, C programming alloc function or alloc system call, if you want to call it, which can allocate dynamic memories arrays on a stack. Okay. So that is why there are generally two pointers which manipulate a stack. One is a start of activation record, one is at the end of activation record. And you can use them to have variable size allocation even on stack.
Sir, but I have one small other question related to this.
Okay.
Yes, it is possible to let's say have a dynamic object on the stack, but at the same time, I mean, in a compiled language like C, the stack layout is fixed, right? When the compiler has produced the code, so I mean, there is not much.
Stack layout is fixed. Who says stack size is fixed?
No, not stack size. A function layout, for example. Let's
again, I also didn't mean stack size. Activation record size.
Oh yes, activation record size. Yes.
Activation record size need not be fixed. That's where alloc comes into picture. Oh, I did not type that. Sorry, I did not press enter. So there is this function called alloc, which is like malloc, but it allocates memory on stack. Okay. In new versions, I mean, nowadays almost every compiler, it allows you to declare an array like this without telling how many elements are there. Okay, or int xn. So you can have statements like this in new versions of GCC. This is probably not standard, but it is acceptable by the compilers these days. So let me just type it out. Wait a minute. The previous one is wrong. The int x which I gave. Scanf, and then you can have int xn. So this is a valid C program, where, at least if not the standard, it is valid with many of the compilers. Okay. Now this int xn, how does it get allocated? Because you don't know at compile time what is the size of x. It could be alloca. Yeah, that might be there. So we can check man page. Okay. So this way array is on a stack, but it has variable size. So what is the advantage of stack versus disadvantage of stack? And actually, if you look at really the architecture, stack and the heap are just conceptual things. It really is the same memory. Okay, one side it is considered as a stack, other side it is considered as heap, and then you grow from both sides. When you allocate something on heap, one side kind of gets the values, and if you allocate on a stack, so for example, let me just use the, so your memory is considered a very large contiguous array. Part of it is reserved for certain things, but then remaining part, what remains in data section, it grows from one side as a stack, and it grows from other side as. Okay, with stack, the restriction is things are last in, first out. Okay, and that is one challenge. If you have an object whose lifetime outgrows its encompassing function, right? So remember, any local variable inside a function, its lifetime can at most be that function. It cannot be accessed outside the function. So then, if the lifetime of a variable is enclosed by its defining function, then you can allocate it on stack. On the other hand, if there is a variable or if there is some location that you want to create in one function but use in another function, then it has to be created on heap. For a stack, when function goes out of scope, basically when function kind of terminates, its activation record is cleaned up, and as a result, any local variable which has been created on stack also goes away. Okay, so in reality, we don't clean up this stuff. We just manipulate certain pointers, like we'll say, okay, currently we are using all stuff up to this, now we'll only use stuff up to this. So this part becomes undefined in some sense. Okay, nobody is going to go there and clean it up with a brush or cloth or anything. Okay, so whatever values remain there, they remain there, and that is why these undefined variables are problem in C programming, because next time when a new function gets called, again your arrow moves down. Now you are using this part of the memory as well. So if you are not careful, if you have not initialized those things before using, whatever is there from the previous time this memory was used will come back. Okay. And again, conceptually, that, I mean, practically that is what is supposed to happen, but you should not even depend on that fact. Because in between, some other process might have come here, used this physical memory, might have put its own stuff. So it's not necessary that your program's last function calls stuff will remain here. It could be anything. Okay. So when the lifetime of an object goes beyond lifetime of the function which has created it, at that time stack allocation does not work. You have to use heap allocation. And this is the kind of guarantee, that's what heap is, where you have to do explicit allocation and kind of explicit deallocation. Again, I'm saying kind of explicit because garbage collection is not really explicit, but it is depends on other factors than function execution. Okay. So memory management for global variables, virtual things which go into your static section is trivial because you are never going to throw these things away. They are global for some reason because they remain there throughout the program. Okay. For stack variable, as I said, it is kind of trivial because it is attached to your activation record. When function gets activated, its activation record gets filled, and when function terminates, its activation record is conceptually removed. So automatically memory management happens along with the activation record. However, for heap, we do not want to tie it to activation record because we don't want it to become used, go out of scope or go out of use after function is terminated. Similarly, we do not want to put it there forever. Okay. Otherwise, we will end up using all the memory and many programs may not be able to run. So any query about this, any question about this? Are they clear or not? So note that in a system, total amount of stack memory plus heap memory is constant. In a constant in the sense, once your program starts executing, there is certain part which is allocated as heap plus stack memory. Okay, at any given time, your total heap memory plus total stack memory cannot cross that amount of memory. It can be different for different programs. Okay, so the maximum allocatable heap memory plus maximum allocated stack memory has to be less than or equal to something. Individually, they can grow as large as possible as long as the other guy is small until they cross that limit. Okay. Yashas is asking, is there performance penalty for using dynamic memory on stack? So there is a minor penalty for allocating it, but there is no penalty for deallocating it. Again, you don't have to explicitly deallocate it. It goes out of scope. So that's a good question. Aren't offsets to local variables and temporaries fixed at compile time? If there is a dynamic stack allocated object, then compiler has to emit more instruction. Yes, so that is also there. So there is some penalty for accessing them as well, because the generated code will have more offsets. Okay, so that is also there. So yes, you are right. But once again, the way compiler lays out things is all the dynamic memory typically goes to the end of the activation record. So your plain local variables, they still end up having fixed offsets. It is just the offsets of dynamic locations which can change depending on what the values of these dynamic arrays are, or sizes of these dynamic arrays are. Okay, so in Aho Seti Ullman, there is a small section on which describes how dynamic sized data, or in fact very large sized data, is allocated on a stack. See, again, if you have a very large array, if it is in between local variables, it might end up causing problem because you will lose out on this locality for various variables. So you want to move this large array to one side of the activation record, large data. So yes, that was a very good point, and it does affect performance, and that is why. But on the other hand, the performance will be much better compared to if you replace this by heap. Okay, because two reasons. One, you have to manage that memory, deallocate it, remember to deallocate it and all. And secondly, again, heap, it's it's far away. Okay, so it might end up being even more slower. Okay, so now we come to this management of heap memory. So clearly for heap, allocation is always by programmer. Okay, at least in C++ language. There are languages where almost all the memory is in heap, all the constructs are on heap, where even allocation is automatic, like Haskell. Okay, so when I say automatic, once again, when you use the when you have to have some kind of use, then it will automatically create the object. You don't have to say new every time or malloc every time. In C++, to create an object, you have to say malloc or new, and similarly to deallocate also, you have to say delete or free. Okay. So programmer has full control over dynamic memory. So it has advantage like having a car or bike with gears, you have full control over how you run it, but then it has disadvantage that you have to have full control over how to run it. If you put a wrong gear, bike or car may stop. Okay. So what are the strengths? Again, it's from a compiler perspective, it is comparatively easy. You just have to give those functions to the programmer. Okay, and then let programmer decide when to call them. So you just need a working memory manager, basically malloc and implementation of free and malloc. I'm not saying it is trivial, it is relatively easy. And then it also allows programmer to decide how to use this memory, how to optimize it. Okay, there are different allocation schemes. If you expect a large number of memory is going to be allocated in next few maybe next few statements, you can pre-allocate it and then use it. And you can also have different kind of actual allocations. Okay. On the other hand, it makes things difficult as well. So one of the challenges, memory leak, basically, and especially this happens in introductory programming courses or simple programs when people write, they will allocate resources, but they never free it. Okay. This is a challenge, not in small programs, but in large programs, especially programs which run forever, kind of your browsers and other stuff, browsers or some kind of web servers and things like that, which run for a very, very long time. Okay. In fact, memory leak has been a kind of a troublesome thing in browsers. Many of us never shut down our system. So and then browsers are also running. Nowadays, I see this problem happening relatively infrequently, but there were days when if you leave Firefox on for 2-3 days, your system will freeze because it will continuously leak memory. A bigger challenge is double freeze. When you are trying to free memory, but your friend who has written some other part of code has also freed it. Maybe it could happen only under a very rare scenario. Okay, some path which is taken very rarely. But then if it happens, then it causes problems. Okay, it is a security risk. And another security risk is somebody has freed it, you don't know it, and you are still using that memory. Okay, so deallocated memory is still in use. So this is also a security risk. And why this is security risk, both of them? Think about it that you have a land which is lying there. Okay, and now nobody knows that you have. I mean, nobody owns it. And you think you will create a house there, you go there, create a house, but next day either municipality or some other goon or somebody comes and destroys your house, okay, or put something there, something illegal in that house, because there is no control. You don't have any control over it, really. So programming languages that have manual memory management are almost always not type safe. That we know about C and C++. They allow programs which are not guaranteed to be safe. Okay, so the alternate we have is automatic memory management. In this case, generally allocation can be automatic or manual, but the deallocation or claiming of memory is automatic. Okay, so how does this work? Now, if someone has to come and automatically clean the memory, they have to have some idea about what is useful and what is not useful. Okay, so again, analogy, if a garbage person, the person who collects garbage comes to your home and collects things which are useful to you, then it will be a very bad scenario. Okay, you won't trust this person. So what you want is a person who can understand what has really been thrown out and what is still useful for the household. So similarly, for runtime management, you want the memory management system to understand the difference between something which is useful and something which is not useful. So advantages, now it takes away the burden from the program. So you don't have to worry about reclaiming the unused resources. But then disadvantage is again, it's kind of a service which cannot happen all the time. It will happen at regular interval. So if between those intervals you need memory, it might happen that you are unable to claim it. Okay. However, I mean, it's not as simple as that. It won't generally happen that you need memory, there is garbage and you are unable to use it, but you don't have much control over it. Okay. So how does system know what is garbage? What are the objects that won't be used? That's one of the challenging question in garbage collection. And secondly, even if it has an idea about what is garbage, how does it actually find these garbage out? Okay, so there are two things. One, you define what is garbage. Other is you really have to go ahead garbage. The ideal definition is an object is garbage at some point during execution if it will never be used again. Okay, so this is the ideal definition. However, in practice, this definition is not used, and we will see why. But let's look at this simple example. So we have few objects being allocated. What are the objects that are garbage at line A or point A? So you can see that at point A, I am doing something with X and I am also doing something with Y. Okay, so if I'm at point A, if I look down, there is some use of X and there is some use of Y. So the corresponding objects are not garbage. Okay, they are useful at this point. What about point B? When I come to point B, if I look down, I see that in future, I am never going to use this object which I allocated here X and the object I allocated here Y. Okay, so both these objects are garbage at point B. Even though I am using variable Y, you can see that I am not really dereferencing the object I created here. I am merely reassigning the object. So I am overwriting the old value. Okay, so the object which I created here is indeed a garbage. This object which I am creating between B and C, can you call it garbage at point B? Probably not, because it's not even there yet. Okay, it will be created at point, let's say B prime after B. So at point B, I can only call these two as garbage items. What about point C? Assuming this is my full program, all three objects are garbage. Okay, so depending on which point garbage collector runs, if it runs here, it will not collect any garbage. And assuming we have a very ideal garbage collector, if it runs here, it will collect both this object as well as this object. If it runs here, okay, if it runs here for the first time, then it will collect three objects. But let's say if it runs here or as at point B as well as point C, then it can potentially only collect this object, not the other two. Okay. So this is a very simple, trivial program, straight line. So nothing is challenging here, and we are doing things manually. In reality, this will be complex because you have function calls, you have branches, you have recursion, you have loop, and all those things. So as usual, from NP hard, we come to undecidable. So once you have pointers in your program, almost all properties of interest become undecidable. Okay. Many things about pointers themselves are undecidable. So any non-trivial property of a complex programming language, of a program in a complex programming language, is more or less going to be undecidable unless you put a lot of restrictions. Okay. So we have to rely on conservative approximation. And as I said, we cannot figure out what garbage is. The earlier definition is ideal definition. So what is an approximate definition? So an object if it can be reachable in the program, then it is considered useful. If it is unreachable in the program, then it is considered garbage. Okay. So in some sense, when you have a program, you stand at a given program point P and you look at all the memory locations that are there. So this is the set of all the memory locations. You will see that your program can only access from P onwards, it can only access a certain subset of these memory locations. Okay. So this is what we call a reachable subset. So these are the things which your program can access if it wants to. Okay. But really your program is fixed. Someone has already written it. So there is another subset of it, which is, it should not go outside, another subset of it, which your program actually accesses. Beyond program point P in some run. Okay. So this is the really useful part of your program, and all these things are garbage other than shaded portion. However, because figuring out the shaded portion is undecidable, most means all garbage collectors, they assume only this part is garbage. So let me change the color. Okay, things which are not reachable, they consider everything reachable as useful. So this is the approximation. Okay. So the major task of garbage collector is to detect and reclaim unreachable objects. And again, with some programming practice, you write programs such that this gap between reachable and usable objects or useful objects is minimized. Okay. So basically, if you read about good programming practice, you will see that in Java, they say that you should always set your references to null once they are used, once they are no longer in use. Okay, so that is the idea. So any question up to now? Any queries? So you have your entire memory. Within entire memory, you have certain part which is reachable. And within that reachable part, you have certain part which is useful. Okay. Ideal garbage collector should collect everything that is not green, but real garbage collectors only collect things which are between red and blue. And again, this is itself is not so trivial. It also and it's also time consuming. Okay, so you want to have efficient algorithms. So generally this part which is in white currently in garbage collected language, this is also called as memory leak. Okay, unlike manual garbage collection, unless manually managed languages, where if you don't free something, that is called a memory leak. In this case, since we are not freeing anything, the difference between reachable object and useful object, it is considered as memory leak in garbage collected language. Okay, so one way to have lot of memory leak is never set any reference to null and keep creating a huge amount of memory and not use it at all. When I say creating, I mean allocating. Okay. So some assumptions we have to make, and again, there's someone I think I kind of get confused because I am also teaching another Python class. Someone in one of these two classes has mentioned that why can't we have C++ garbage collector for C and C++? So there are people have made garbage collector for C++, but then they also are approximations because of one very big challenge. C++ like language allow you to create pointers or references from nothing. Okay. So at runtime for garbage collected language, we should be able to find all existing references in the program. Okay. It is very difficult or in a way impossible in C++ language. Because in C++ language, an integer is indistinguishable from an address. Okay. Yes, types help us, but as you know, in C++, you can always typecast integers into addresses and back and forth. So that becomes very, very difficult to decide whether a number that you see in your program, is it really an address in the heap, or is it some number that you just want to print? It's the amount of bitcoins that you hold, or it is the price of bitcoin that you have. So you don't want your garbage collector to treat all your bitcoins as garbage. Okay. So if you know all the references, then it allows you to kind of introspect, basically look at the structure of your program as well as memory easily. Okay. So two assumptions: you cannot fabricate a reference to an existing object from nothing. It has to be there in the program itself explicitly. And secondly, you cannot cast pointers to integers or vice versa. Okay, so you should remember these. And C and C++ are languages which violate these assumptions. Okay, so any queries, any questions? If something is not clear, why these assumptions are there? Okay, right. So let's move forward. So I'm seeing the number of participants has reduced as well as number of queries have reduced. So I think people have got good lunch. We don't have any control. Generally, when we conduct physical conferences, we provide very bad lunch so that people don't sleep. All right. So now just some kind of information about existing garbage collectors. So garbage collectors can be divided into two categories or they can be divided along several different properties. So one kind of category is incremental versus stop the world. I think the name itself tells you what is the difference. So an incremental garbage collector generally does not stop your program from executing. Okay, so your program is running and you know that most of the systems today have multi-threading or multi-core systems. So garbage collector runs as another thread and then it collects while your program is executing. On the other hand, a stop the word garbage collector, it stops your program from execution for some time and then it collects all the garbage, it does some changes and then allows your program to run again. Okay. So now there are questions to think about. In general, okay, which one you think will be more precise? More precise means it will collect more useless references. What is your thinking? And why? I mean, you can, again, there's no wrong answer. It will depend on what is your logic or what is your reason to select one. You can select either.
I think incremental should be faster.
Incremental will be faster. What about precise?
Oh, okay. Preciseness is also, I think incremental should be more precise because the reasoning behind, I'm assuming, is that we will be considering the, let's say, garbage collected to be garbage collected object one by one, right? That's what I meant by incremental. Is it the other way around that?
No. So
I mean,
again, difference is, suppose you are running a program. Let's say you are running a large simulation. Maybe you have created a game and the game is running. People are playing. And for some reason you need memory. Okay, your particular system needs memory, more memory, and let's say it's a garbage implemented in garbage collected language. So in case of incremental, you still can play. You can still kill some opponents or build some buildings and so on in the game, while garbage collection is going on in the background. Okay, in stop the world, your program will stop. Maybe it will allow you to read things, it will allow you to see things, what is there on the screen, but you won't be allowed to create a new object, or you won't be allowed to destroy a new object. Your thing will kind of get frozen, and stop the word collector will work, and then it will allow you to proceed further. Okay, so in a way, you are you cannot access the memory, heap memory, while garbage collector is running at all. You cannot access it at all. So program pauses in a sense.
Then I think, I mean, stop the world should be more precise, because we have a frozen view of memory that no new transaction will come. Let's clean up, then we will start the process again.
Right. So in a way, you are stopping everyone from creating or destroying the new garbage. Okay. So that way, stop the word collector is much more precise in general. What happens in incremental? I mean, you will always be able to clean up part of memory where your program is currently not executing. Right. See, incremental cannot go ahead and start clashing with your actual program. So some part of memory it will mark as in use, and it will only collect garbage from rest of the part. Okay. So it's not as simple as that, but that's the kind of thinking. It's like you're cleaning your home, and some people are walking around with the dirty shoes. Okay. So how do you make it? So clearly, if you stop them from coming inside house, your house will be more cleaner. So generally, stop the world is more precise. But what is the challenge? So what about if you are having a nuclear reactor control system, or some system which is controlling Mars rover and so on? Okay. The problem there is you cannot stop connecting to those things. You cannot stop them. What if during that few seconds something bad happens? Okay. So certain parts should still continue to run, certain part of the program. So in such cases, you may not want to stop the world collector. Okay, you still want to collect data which is being sent. You still want to have some control commands being sent and so on. So in such cases, you might want to go with incremental collector, and you will make sure that there is enough buffer so that you don't go out of memory while your program is running as well as collector is running. So there are some lot of engineering decisions which have to be made. At what point your garbage collector starts executing? You cannot start it after you have exhausted all 100% memory. Okay, because then garbage collector will not find any place or any space to run itself. So in general, garbage collected languages, their runtime system reserves some memory, okay, or certain percentage of memory, so that garbage collector itself can work. Sometimes it can be as bad as 50% of the memory, or more than 50% is reserved. We'll see that. So the other kind of garbage collection categorization is based on whether they are moving objects around or not. Okay. So just, I mean, I don't know, nowadays we don't see that. Earlier there used to be these file compactors in Windows, which used to have very nice animation. Suppose I have few objects in my memory sitting here, 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 and then there are few which are now garbage. So these shaded ones are garbage. Okay, and so after garbage collection, do you get your memory look something like this, that all allocated objects are nicely sitting together? Or is it just that garbage collector has simply removed the garbage objects from the consideration? I mean, in a way, it has taken it away from the program. Okay. So compacting garbage collector is this one, which also moves object around so that all allocated objects are sitting together. A non-compacting collector is one which will leave all objects where they were. It will simply remove objects which are garbage, but useful objects will remain at their own place. Okay. So once again, why do we want one versus other, and which one will spend more time in collection, which one will lead to faster program execution typically? Any ideas, and why? Anyone?
So compacting will spend more time because it has to move stuff around, and non-compacting should be faster.
Yes. And which one will be faster? Not garbage collection, faster program execution.
Yeah, the non-compacting one, because I think,
Non-compacting one.
yeah, because it won't be moving stuff around. So
No,
that's
so, okay, so garbage collection will be faster in non-compacting. What about the actual program? I mean, if you remove garbage collection type.
In this case, compaction should be faster, right? Because now the objects were placed in a, let's say, aligned fashion, so they can be accessed easily and will result in faster memory access.
Yes. So again, if you randomly put them together, probably it may not. I mean, it will be really a lottery whether it is faster or not. But as we will see, compacting garbage collectors typically put related objects together. One which is referencing other will be together. So that also gives you locality of reference. So after compaction, program runs faster. Okay, but all these are kind of a statistical event. I mean, it's you can always create program which will go against the general thing. Okay. So another thing is, not all programs or not all languages will be amenable to compacting collector. The reason is these addresses are changing. Okay. So if languages depend on address of objects, directly depend on addresses of object, then having a compacting collector is going to be a big challenge. Not only you have to change addresses in memory and then in memory pointers, you also have to search all the variables in the program and figure out which one of them is holding the addresses and then update them appropriately. Okay. Now that's why generally compacting collector works for languages which have references and does not allow programmers to directly manipulate addresses. Is it clear?
Yes, sir.
Yeah.
Uh,
A little louder. Yes, Nish.
yes, sir. I'm saying it's clear. Like I was just.
Okay, thank you, thank you. So now let's look at some of the methods of garbage collection. One of the most simplest, probably many of you might have used it or at least heard about it. It's called reference counting. Okay, very, very intuitive. How do you figure out something is garbage? Basically, you keep track of how many people are pointing to it. So note that we cannot keep track of usefulness of an object. It's very complex. Okay, it's undecidable. So what we want to keep track of, whether an object is reachable or not. So we just count how many people can reach it. Whenever that count becomes 0, we will consider the object as a garbage. So it's a very simple framework. It requires you to store a reference count to keep track of how many references exist to an object. Okay. Now, whenever you create a reference, how can you create a reference? By assigning it to some other object, by passing it as a parameter, because you will create this formal parameter will start pointing here and so on, or you explicitly take address and many other ways. Okay. So you'll have to capture all such constructs in your language. Anytime such a construct is executed, you have to find out which object it refers to, increment its counter. And similarly, you'll have to find all possible constructs that can remove a reference. So for example, when you return from a function, so all parameters, their count should decrease, and so on. Okay. So while doing this, once an object reaches 0 count, then you can clearly see that there is nobody who is referring to it, and therefore such an object can be reclaimed. Okay. Now it can happen, as we'll see very soon. Maybe object A, its reference count became 0, so you reclaim it, but then object A was pointing to object B. So object B's reference count also has to be decremented when you reclaim object A. As a result, it could happen object B also becomes unreachable. So you claim that as well. Okay, so this might decrease other object counts and trigger more reclamations. So here is a very, very simple example. We are creating a linked list with 3 elements and then we are manipulating it. So when we create first element, head points to, so head itself sits on stack. Head is a variable. Okay, it holds a reference to an object in the heap. So this is Java-like program. So you have to understand difference between reference and pointer. Okay, so head points, it's like a pointer which points to an object in the heap. So, and because head, so initially when the object is created, it will have a reference count 0. Right hand side gets executed, object gets created, reference count is 0. This assignment takes place. So clearly assignment adds a new reference. So reference count increases. Okay. Same thing happens with mid. Same thing happens with tail. Then I say head dot next equal to mid. What is happening? Head is now pointing to mid using its next pointer. But then it means also that count of mid increases by, or the count of the object, reference count of object, which referred by mid increases by 1. Okay. Similarly, for the next assignment, now after that I set mid and tail both to null. So I am kind of removing these, retracting these references. As a result, number of references to those corresponding object also decreases by 1. Okay. Finally, I said head dot next equal to null. So I am retracting this pointer here or reference. Okay. As a result, the object, its reference count is decreased and it becomes 0. Which means whenever next time garbage collection runs, so it need not be instant, okay, or it can be instant. So in case of reference counting, you have the choice because you're in a way you have these reference count getting manipulated. So as soon as it becomes 0, you can claim it, or you can just leave it there. Whenever next time some garbage collection happens, it can check all the reference counts and claim it. Okay, so you can reclaim it. If I set head equal to null, this pointer gets retracted. So head pointer pointy object, its reference count became 0. This gets reclaimed. As a result, this also becomes 0. So this also gets reclaimed. Okay. So you can see that it's quite simple that way. The challenge lies in identifying all statements which manipulate references. Okay. So assignment is one of them, but as I said, there can be others. Okay. So what is other challenge in reference counting? So this is very quick algorithm. I will skip it. There is one even major problem. Okay. So as a designer of the language, you will know what are the statements or the construct with manipulate references. But then there is a major problem, and here it is. So similar linked list we have created. We have created all these links. Okay. Now what we have done, we have created a circular list. So tail.next points to head. And therefore head also has, or the object corresponding to head also has its reference count to 2. At this point, I retract all the variable reference variables, their pointers. So head becomes null, reference count becomes 1, mid becomes null, reference count becomes 1, tail becomes null, reference count becomes null. Okay, so this is the problem. You have a set of memory locations which are unreachable, but it just so happens that they all point to each other in a cycle, and therefore all of them have non-zero reference count. Okay, so this garbage collection this garbage cannot be identified and collected by our simple reference counting based garbage collector. So you are having real memory leak here because they are not collected, they cannot be even reused. So you have kind of lost this much memory in your system as long as this program is running. Okay, so yeah, so this is one of the major problem. And as you know, I mean, circular lists are not that uncommon data structure. And not just list, any data structure where you have circular references can have this problem. So if you have tree where children node point to parent node, will end up having similar problem. So this is a genuine problem. Okay, so how do you fix it? One is, of course, you go to some other method, but many times if it is not that major source of an issue, when it happens infrequently, you can have a separate pass which goes over all such searches for such cycles and kind of forcefully reclaims them. Okay, but yeah, so those can be done. That kind of things can be done. So any question? But classic reference counting will have this problem. You have to have some explicit way of handling such cases. Right? So what we are having, a reference cycle, which is a set of objects that cyclically refer to one another. And because all objects are referenced, all have non-zero reference counts. Okay, and the issue is that reference count track number of references. It does not track number of reachable references or number of references which are reachable from program variables. Okay, and as I said, I mean, it's if in a system these things happen infrequently, you can still use reference counting based garbage collection, which is quite easy to implement, simple to implement. Okay, and there are languages which use it. Why they use it? Because once again, the program, they expected that, okay, if this becomes a problem, it's not a very big deal. People can always restart the browser, okay, like Firefox. So you should not be using it in a mission critical system. So advantage, simple to implement. You can even implement as a library on top of explicit memory management. So basically you kind of hack into all your memory management routines. Okay, so any sharing of references will result into incrementing reference counts. The disadvantage, you may fail to reclaim unreachable objects. Now, as we saw in our linked list, we had only 3 elements, but first element triggered second element reclamation, second element resulted in triggered reclamation of third element. So now if you have 1000 element linked list, it will be really slow. Okay, things are happening one after the other. And third thing, because any assignments or any construct which shares references has to do these reference count updates, it slows down. Okay, so every assignment kind of becomes its cost doubles. Not only you are doing assignment to the pointer, you are also doing an assignment or increment on the reference count. And finally, there is another disadvantage. You see that you have to have some space for storing these references. So how big this space should be, all those challenges are there, but you are kind of wasting little bit of useful memory, okay, to have reference count. But as we will see that it's not a big disadvantage, because no matter what garbage collection method you use, you have to have some space for bookkeeping. Okay, you cannot have garbage collection without memory, without using memory, certain memory. So if there are no questions, we will move on to the second kind of garbage collector, which is called mark and sweep garbage collector. And these are very, very practical garbage collector. Majority of the languages implement it. And we will see that. In particular, finally, we will hopefully come to those slides which show the practical garbage collectors. They really use not a single mechanism, but a combination of mechanisms. Okay, it's like for certain part of memory, you use reference counting, but then for some other part, you use some other thing. And when you really have to do very precise work, then you go for mark and sweep because it's a little costly. Okay. So reachability, we have to find what cells are reachable, but reference counting failed. So mark and sweep, what it does is it works on what is called a set identified to be a root set, which is the set of memory locations in the program that are known to be reachable. Okay. So when you are designing your language and you are designing the runtime system, you have to define a set of memory locations which are known to be reachable. This is where you start. So for example, in a Java-like language, what can be your root set? Where will you start collecting garbage? Things which are guaranteed to be reachable. So any answers? So you need to start with certain memory locations that are guaranteed to be reachable. So what could those locations be? You are running a Java program, you are deep inside the function, maybe main called F1, F1 called F2, F2 called G3, G3 called H4, and suddenly you needed memory, so garbage collection got triggered. At this point, garbage collector has to figure out what is reachable, what is not. So where will it start to look for reachable objects?
It could be harder to tell because this is all executing on a virtual machine, right? JVM. So it could be harder to tell for at least.
So again, Gaurav, let me rephrase my question if it is not clear. I'm not saying you should know all the reachable objects, but I want you to start with certain objects that are guaranteed to be reachable, that are known to be reachable. See, there is a big linked list. Okay, you can start with the head of the linked list, right? If I want to ask you that, okay, where will you start if you want to traverse a linked list? So you will always start at the head, which is known to be reachable in the variable head, and then you will move forward. You will check head.next, and so on. If you have a tree, what is something that you have to have in hand so that you can process this tree?
Root.
The root node. Okay. So generally, where will you store this root node? In a Java program.
In a function. It will be allocated inside some function frame, right?
Allocated, but it will be stored somewhere, right?
Yes, stored. Yes.
Variable.
Yes.
So you can always start with variables. So basically, local variables, not just current function which is executing, but also all the functions that are on activation stack. So basically, you look for all the variables which are there on the activation stack, whether they belong to current function or to the function before that or before that. What else? So in case of Java, you have to look for all those static variables. See, static variables, they are always reachable in some sense, right? They are always alive. Global variables in other languages. So you can think about global set. Okay. Then there are certain things which you should look for, certain data structures like hash table. If you have a hash table in your program, okay, or a set in your program, then the things which are reachable from that set and so on. So you will have to think about things where you start. So in Java, root set is typically all the variables which are on stack as well as all these global and static variables. Okay, few more things can be there, parameters and other stuff, depending on how you implement it. You can think of them also on a stack. Okay, so any objects reachable from the root set are reachable. Now think about it. Is it possible? So once we have taken care of this root set, anything that cannot be reached from root set will be unreachable, directly or indirectly. As long as something is directly or indirectly, means through multiple steps, reachable from root set, that cannot be considered garbage. Whatever remains will be considered garbage. So the idea of mark and sweep is you start with the root set, you mark those root set, and then you mark things which are reachable from root set. Now you mark things which are reachable from this reachable from set, and so on and so forth. Okay. So in a way, you do a graph search. So mark and sweep, it will run in 2 steps or 2 phases. First phase is just a marking phase. It starts with the root set, and again, probably Professor Srikanth might have talked about work list. Work lists are very useful data structure. So they are not really a data structure in the sense of queues and stacks. You can use either queue or stack to implement a work list. But in the sense that with work list, you push work to be done. I mean, nodes which require certain processing in the work list, and you pop out them one at a time. And when you process this current node, you might end up getting more nodes which require work to be done. So you will keep on putting them inside the work list. Okay. In general, the order in which you push and pop, so I should not call push and pop, in the order in which you put elements in work list and take them out need not be defined. You can take out any element, process it, put more elements, again take out any element, and so on. Okay. If you put certain order, then you get things like breadth first search versus depth first search, in which order you are putting, in which order you are taking them out. But in general, as an abstract entity, work list does not define in what order you are taking things out. So it only you only worry about work list containing certain objects. Okay. So how does marking phase work? Initially, you add every element in the root set to the work list. These are the things which are guaranteed to be reachable. Then you process one element at a time from the work list. You remove it. If it is not marked already, you mark it and add to work list all the objects that are reachable from this current object. Okay, so this is your tree search. It's something like this you have done for breadth first search or depth first search. Okay, it's almost like a search. Okay. Now, once this phase is over, and assuming your root set is identified properly, you have marked all the objects that are reachable from root set. Now, sweep phase goes through every single thing in the memory. Okay, every single object. If every single allocated object, I mean, if that object is not marked, it is removed from allocated objects, so you reclaim it. If the object is marked, you will unmark it so that it is ready for next mark and sweep. You cannot leave that mark around. So if it is not clear, let's go and have an example. So this is my allocation in memory, lot of objects. This yellow thing will be used for keeping mark. Okay. And I have just one element in the root set. In practice, there will be multiple such elements, and you have to do this thing for all elements of the root set. There can be sharing, like we can see this object is shared by 2 objects, this object is shared by 2 objects, and so on. Okay, it does not matter. So initially, root set goes into work list. So things pointed by root set, you have to mark them. Okay, put them in the work list. Put the next whatever is pointed to by that in the work list, mark things. So that's how things will work. So now you have in work list this object. You are looking for everything that is reachable. So this happens to be only this object. So it goes into work list. Okay. And now what happens? You will take out the element. So this object is in the work list. You take it out. Since it is unmarked, you mark it. And then you put all objects that are reachable from this onto the work list. Okay. Once again, you pick one of the objects, view it. If it is not marked, mark it. Anything which is reachable from this will have to go into the work list. So, I mean, animation is not exactly perfect. I think this should have come in the work list, or probably it will. Yeah, it has come. So first thing I'm moving it and then pushing it. So it looks like it is a queue-like work list, first in, first out. Okay, then this is marked. You try to push this element to work list, which is already there, so nothing happens. In fact, here it is showing in. So either you can check in the work list whether it exists or not, but here it is. So this is someone else's slide, so a little bit of confusion for me, but I think the idea should be clear. Okay. Now there is nothing, the object is already marked, so you just remove it from the work list. At this point, you can see that whatever is reachable from root set is already marked. These two objects, even though they themselves refer to others, there is no way you can reach them using root set. Okay, so these will be reclaimed. Okay, so when sweep phase starts, it goes over individual objects. If those objects are not collected, if those objects are not marked, they will be reclaimed. And the objects which are marked, their mark will be removed. Okay, how you do it is again implementation detail, but that's the idea. So any questions? Okay. So when we try to implement mark and sweep, you can see that it's not a very efficient algorithm in the sense you have to go through all the allocated object. Okay. So its runtime is proportional to the number of allocated objects because sweep phase has to visit all objects to free them and clear marks. And secondly, work list can also be a bottleneck. It requires a lot of memory. In our example, at a time, there were only 2 objects in the memory, but you can clearly see that if you have a practical program, there can be a large number of objects. If you are talking about tree-like things, I mean, multi-array tree. Okay, so you don't know a priori how many objects can potentially be in work list, so you cannot allocate, you cannot reserve some space for it, which means you have to kind of be little alert to execute your mark and sweep at regular intervals, so that you still have enough space to maintain your work list. Okay. So there are some implementations which can improve mark and sweep. I'm not going to go into detail. It's called Baker's algorithm, which takes advantage of the status of each object and creates linked list of these objects. Okay, so it does not maintain an explicit work list. Okay, but what happens? It has to have some space for having next and previous links. Okay, so you are, as I said earlier, reference counting, reference space was not a problem because even other algorithms will require some space for bookkeeping. So implementing mark and sweep will require you to either have a space for work list, it will require you to have space for marking the memory, as well as it will require, if you are having some efficient implementation, it will require some more pointers. So next and previous in this case. These are not program pointers. These are only accessed by garbage collector. Okay. So this I won't go into detail. I want to go through another algorithm called stop and copy. So another thing you have to tell me about mark and sweep. Is it a compacting algorithm or a non-compacting algorithm? So this is a quiz. Anyone? What do you think? Is it a compacting algorithm or a non-compacting algorithm? Whether you look at it this way or using this way. So is there any, yeah, go ahead, somebody I think has unmuted. See, we have objects, we are marking them. While sweeping, if mark is there, we leave them untouched except cleaning the mark. If the mark is not there, we reclaim them. So we are never moving around objects which are marked. Okay, we are simply either setting a bit or clearing a bit or a set of bits. So we are never moving objects around. So what kind of garbage collection is this? Is it compacting or non-compacting?
Non-compacting.
Non-compacting. Okay. So then we look at another algorithm, which is a compacting algorithm. So stop and copy, as we'll see, it increases locality because it will move objects around, and in a way that objects which refer to other, and two objects where one refers to other will be kind of adjacent. Okay. And it also helps in increasing allocation speed. Okay, because all the free list, the free objects are also sitting together. You don't have to do a lot of manipulation in maintaining free list. Okay. So now the challenge is that because we are compacting, garbage collector also has to update all pointers in all objects that refer to the new object locations. Okay, and as I said earlier, this kind of things are easy in Java because Java, you don't get explicit access to pointers or addresses. Okay, you cannot store address of an object anywhere. Okay, it's not allowed per se. But in C++, you can manipulate addresses explicitly, and therefore you can even write an address down in a file and later read it to decide which object to dereference. Okay, so it's impossible for a garbage collector to find out all possible ways when an address is stored in a C++ program. Okay, so that's why this kind of garbage collector, even if you try to implement it for C++, you will probably end up implementing a non-compacting garbage collector. So I just gave a hint. Usually implementation of malloc and free use free list, and they manipulate this linked list of pointers or objects. Okay. So allocating an object requires chasing these pointers, moving them around, and then again finding a suitable object. In contrast, when we look at this copying based collector, we'll see that you just have to keep moving what is called a free marker. Okay, free list marker. So again, it's not possible to go into the complete details. So we'll only look at animation. So when you have this kind of stop and copy garbage collector, you have to divide your memory into two parts. Okay, and immediately you can see the disadvantage of your stop and copy collector. You can only use 50% of useful memory. In fact, it will be slightly less than 50% because you will also have to maintain some more data structures to run garbage collector. But it is approximately 50%. So only half of the memory is useful at any given time. So we divide this full memory into two space. One is called new space, other is called old space. Sometimes you will hear terms like from space and to space and things like that. Okay, but it does not matter. The names do not matter. So this is sometimes it is called from space. Because during garbage collection, we will move things from space to space. So how does things work? So initially, let's say everything is empty. And this is our current space. This is our auxiliary space. So let's say we start in the left side of memory. We just have a simple pointer. Anytime an allocation request comes, we allocate the sufficient memory and move this pointer forward. Okay, free space, just move. So you can see how quick this whole thing can be. It's nothing but just incrementing a pointer, one instruction, that's all. Let's say another object is allocated, another object is allocated, and so on. and second object points to the first object. Then you allocated a large object, but free space should be slightly more to the right. But I think you get the idea. Okay, and things like that. At this point, after green stuff is allocated, maybe we want to allocate another block, but there is not sufficient free space. Okay, so now somebody asks for some more memory and there is no more memory remaining. Assuming our root set points only to the yellow object. Okay, these things were created, they were in the root set for some time, they're pointed by root set, but maybe at the point of last allocation that I asked, root set only points to yellow object. So some of these objects have become garbage because they are not reachable from root set. In particular, you can see that from yellow I can reach pink, from pink I can reach green, from green also I can reach pink, but that's all. I am not reaching blue object, I am not reaching this gray object at all. Okay, so I need some way to reclaim this memory. So how will things work? Stop and copy will stop program from execution at this point. It will put it in suspended state. It will start copying things from root set. So first root set got copied. Now anything that root set refers to will also get copied. So this pink object gets copied and you keep doing this recursively. So now pink refers to green. So green gets copied. Green refers to pink. But then we kind of will maintain this somehow that pink is already there. And that's all. Okay. After all this is done, or sometime you have to also manipulate the pointers that yellow thing points to this new pink, or new yellow points to new pink points to new green, and new green points back to new pink, and so on. Okay. Other things which are not useful are not copied from old space to new space, and therefore that memory is kind of reclaimed. Once copying is done, you move your free space and your root set. Okay, so root set now points to the new location, free space points to the new free start point, and this part, even though it still shows colored thing, it is conceptually being reserved for next run of garbage collection, when this will act as two space. This will act as the place where everything will get copied to. Okay. So this is the idea. Suppose we allocate more objects. Once again, we run out of memory after some time. At this point, garbage collection starts again. So we copy yellow thing. We copy red because now yellow points to red. Then we copy blue because red points to blue. Blue points back to yellow. So we need not copy anything else. Okay. And once again, we have to set root set as well as free space. And we have to treat this right side space as being reserved for next run of garbage collection. Right? So any questions about how it works, at least conceptually? Okay. So one of the challenge that we continuously discuss, because pointer themselves, the addresses themselves are changing. Yellow might be having address 1024 here, but now it is having address 0. Red might be having some address 2056 here. Now it is having address probably 0004. Okay, how do you keep track of these things, and how do you forward put things properly so that they still point to each other and so on? So idea is, I mean, this is just the details. I'm skipping this. So the tricky part is adjusting the pointers. So again, adjusting pointers requires you to reserve some more space, which will help us figuring out where should we point to after compaction is done, after movement from old space to new space is done. Okay, so you can see that we are really dealing with, or we are really allowed to use useful memory, which is less than 50% of the available memory. So this is one of the big disadvantages of stop and copy. So how do we implement this manipulation of pointers? So basically we have in each object some extra space which can hold a pointer. When we copy objects, initially we don't take care of manipulating these objects and their addresses. Okay, first we just do a kind of blind copy of object from old space to new space. All pointers still point to their original locations. So basically your object yellow got into new space, but its next pointer might still keep pointing to pink object in the old space. Okay, once we have copied all objects from old to new, then we will properly set forwarding pointer. Okay, so I will just show you the animation. It will hopefully make things clear. So now this is an extra space for keeping track of forwarding pointer. Yellow is our root set. We are doing garbage collection. Okay, so which means we are copying from filled memory to new memory. Yellow gets copied. Okay, note that this yellow was pointing to green object. Newly copied yellow, since it is just a bitwise copy, it's a blind copy. The next pointer is still pointing to old green object. Okay, at the same time, after copying yellow, we will also set this forwarding pointer saying that the old yellow which was here is now can be found here, is now here. Otherwise things are going to be the same. Okay, because we did the bit copy, next pointer still points to the old object. After bit copying, we set up this forwarding pointer which tells new yellow object can be found here. Now we go on to the objects which are pointed by yellow, which is green. So we will copy green. Now green happens to point to red. So this new green also points to old red. Forwarding of green points to new green. Then we have to copy red. In case of red, there is no next pointer. This is, the pictorial representation of null. So forwarding pointer of red is set to new red pointer. Okay, up to this point, I think things are very, very easy. Now we have to have one more iteration over new space, over all allocated object. I go to yellow. I go to yellow dot next, basically yellow, any pointer that yellow is pointing to. And what I do, I replace this next by forwarding pointer of next, assuming this field is next. Okay, I'm just assuming field is next. So whatever is pointed by yellow is replaced by pointees forwarding pointer. So this brown will actually become brown dotted. So that will fix it to point to the correct green object. And this will always work. Brown pointer points to old object. So what I'm going to say, brown pointer equal to brown pointer dot forwarding pointer. So brown equal to brown plus brown dot forward. So brown equal to brown dot forward. So automatically it starts pointing here. Okay, so this is how manipulation of addresses are taken care of. Okay, and that is why it is important that you are not allowed to explicitly store addresses. I do not want to have a file which contains the address of red object or yellow object, because I cannot go and modify those addresses. Okay, so quickly, advantages, again, simplicity. It's quite fast when you are allocating memory, almost zero overhead. Okay, and it has excellent locality. After every garbage collection, all your objects are allocated together, and as you see that they are kind of allocated, the objects which differ to each other are allocated together, because we go into some kind of depth first order. Okay, but a big disadvantage, more than half memory is unusable. Okay, and collection time will be proportional to the number of bytes used by the objects. So you have to do a bit copy of all the objects. So finally, what do practical garbage collectors do? So I don't think I will be having full time to cover it completely. The practical garbage collectors, they have what is called a series of garbage collectors. Okay, they are based on a combination of smaller garbage collector. Each garbage collector targets a specific types of garbage, and there will be a final fallback garbage collector which will look at everything. So generally this final fallback is your mark and sweep, because it is one of the most precise garbage collector, and which does not use as, I mean, stop and copy is as precise, but that uses lot of waste lot of memory. Okay, and the reason we have multiple garbage collectors is because it's an empirical study which tells that most of the objects which are created, they die young. Okay, you create an object and you lose reference to it, because most of them, the reference is copied during function calls or during a very short lived processing. Okay, so most objects have a very extremely short lifetime, and these empirical studies have also shown that once an object has survived a few garbage collection, like 2 or 3, then the chances of that object having a very large time is very high. So either your object gets collected in first 2-3 garbage collection after it is created, or it remains there forever, almost forever. So very few objects will have lifetime which will go beyond 10 or 12 garbage collections. And once again, one of the reasons for that is the compilers are responsible for it. They create temporary objects left and right. These temporary objects are created and used only once. Okay. After that, we do not use them anymore. So you have seen a lot of transformations yesterday and today, which depend on this, which kind of create temporary objects. Okay. So the garbage collector, when you have series of garbage collector, so you have certain ones which target these young objects and certain others which target tenured or long life objects. So, and these kind of garbage collection is called generational garbage collection. You are maintaining generations of objects. Okay. So the first generation garbage collectors, they run very quickly. They may not be as effective, but as your first generation fills up, you move objects to second generation, third generation, and finally, when even third generation fills up, then you run a very slow garbage collector, okay, which will be run on all the memory. Typical languages will have, or systems will have 3 to 4 generations, but many times even 2 generations give a very good result. So this is garbage collection in Java. It has 3 generations: Eden, Survivor, and Tenured. Okay. Now you can see that it's Eden is like your, could be reference counting based, because it's very simple and you are not very particular about efficiency here. You are not very particular about precision here. Okay. Survivor, you can see that it is like your stop and copy. You are only using half the memory at a time. And finally, tenured, where you will be using mark and sweep. So you create certain objects, then there are some of the objects, garbage collection runs, it reclaims some things, but one object remains, so it can be moved to a survivor object. So here, after even one garbage collection, if an object survives, we are moving it to the next level or next generation. Okay. Again, depending on your applications, you can put some different tenures here. Again, you allocate few more objects. Another garbage collection ran. Another object survived. That is also moved to survivor objects. You keep doing things. At this point, you have one object remaining. Okay. But it cannot fit into survivor objects. So you have to run a garbage collection in survivor objects as well. Probably this is a mark and sweep, stop and copy. So you have moved object from space to 2 space, and you also kind of remember that it has passed through one generation of garbage collection in survivor space as well. Okay. Now this object also comes here. It is also stored in this space, and things happen like that for some time. And once this space is also full, Okay. If a garbage collection run, this object, assuming it is still alive, it will have two garbage collections. It has survived 2 garbage collections, so it will be moved to tenured objects, because empirically such an object is supposed to live for a very long time. Things keep working like that. Okay, so this kind of garbage collection in Java, the new objects are allocated using a modified stop and copy collector in the space. When Eden runs out of space, you move it to survivor space. Something which survives long enough goes into tenured space. Okay. When all of them are filled, you run a full garbage collection, which can collect tenured objects. Now, this full garbage collection is very, very costly. And in Java, in fact, Java runtime system gives you some control. Users can call garbage collection. So they can call a shallow garbage collection, which will only work at Eden or survivor space, or they can call a deep garbage collection, which will collect all the spaces. Okay. So I think I will stop here. I have gone about the time, so I will take some questions. Okay. And again, in Java, because it's a practical language, there are engineering optimizations. You do not wait till these things get full. I mean, for understanding purpose, I am showing that when something gets full, you run a garbage collection. Java has a few other optimizations. It can decide whether to do a garbage collection at certain point or not. Okay. Even users can add their own. You can modify the VM. So there are these VMs like Jikes RVM, which allows users to add their own code as well. So they are open source. You can modify garbage collection thresholds in some sense. So questions? I think a lot of garbage. We need some time to collect it and compact the knowledge we are getting in these 6 days, or actually 10 days for you, not 6 days, 5 days last week.
Hello, sir.
Please, yes, Sumit.
Sir, actually, I had a slightly different question.
Okay.
Sir, for like languages where like garbage collection is not, not done by default, in case of, let us say, in C++, I'm using some STL, or like I have my data structures where I'm allocating them, and I know that I can use delete and free and all that. So
Okay.
like in that context, if like if we want to implement a garbage collector, so do like these primitives or like these algorithms, like can we apply them there, or are there like other techniques or things to consider for languages that don't have a garbage collector?
Okay. See, as you could see, for garbage collection to implement it, only thing you need is somehow find out things which are reachable. I mean, I'm also assuming you are going to implement some classic garbage collection algorithm. Okay, so almost all of them depend on a way to figure out what is the reachable subset of memory. Okay. Now with C++, the challenge is this reachable subset. As I said, you allocate an object, you store its reference in a file. You open a file, you store that address in the memory. So something like this in a file. So let me just write a simple program, again, kind of pseudocode. I say x equal to new. Okay. And then I say fprintf my file and %d or whatever, %x. Sorry, my file should be not like that. So please ignore the syntax, %x for pointer, let's say, and then I store the address of x. Not address, x is a pointer, so value of x. Okay. And I say x equal to null. And I do lot of things. And later I create a variable y in which I read from file. Okay. Now for a garbage collector at runtime to figure out that there is a pointer which has been stored in my file, that is what you are reading here. Okay, in between if a garbage collection happens during runtime. Okay, how are you going to figure out whether this particular location object is garbage or not? Right? You have no
Yes,
way,
sir,
you have
I
no
see.
way this
Yeah.
address is stored. There's no place. Garbage collector cannot go into your file system and check all the files. It does not even know what is happening here. Okay. So that way, because you have explicit access to addresses of objects, garbage collection for C++ like language becomes difficult.
I see. Yes, sir.
In fact, I can even write another thing just after this line. I can say for y equal to 0, y less than x, y plus plus. Okay, I can add this for loop, and after this I say x equal to null. Okay. Now, for all practical purpose, your runtime system might think this is the integer. Okay, but what you have really done is you have kept this address. You have saved the address. So you will have to tell your garbage collector that, okay, though this looks like an integer, it is really an address. So consider this as part of your root set. So all this makes analysis of pointers, in general, analysis of pointers is very, very difficult for C. So this makes the life of garbage collector very difficult. On the other hand, there is a garbage collector written for C++. Okay, I think it's done by Hans Boehm. I will have to check the name. BOEHM or something like that. I will just check. Maybe I can.
Yes, sir.
Search it, and it has some restrictions that what you can do and what you cannot do with the pointers, and still it says it's a heuristic. It may miss out on garbage collector. I think they err on the safe side. So if it thinks something may or may not be a pointer, it will assume it is not a pointer, or probably it will assume it is reachable, I should say. Boehm's garbage collector. Okay, and let me see if this particular Wikipedia may not describe it, but it has a lot of. So you have to include this file. You have to have certain kind of function. So you cannot directly call malloc. You have to use their own malloc,
Yes, sir.
and their memory management function, because it does some kind of bookkeeping, like keeping some extra information about what it points to and so on. Okay.
Yes, sir. Yes, sir.
So rather than writing your own, you can try if this Boehm Weiser garbage collector works for you.
Yes, sir. Thank you, sir. Thanks a lot for answering. Thanks.
So it also depends on type information to locate pointers. Okay, so then I think we can stop here.
Yeah, thanks, Amey. Thanks for some wonderful lectures.